See, from the experiments based on interference and diffraction of light, it was proved that light has wave nature. Right? Wave is basically a disturbance which propagates from one point to another. Now, the disturbance in case of light is in terms of electric and magnetic fields. Light is an electromagnetic wave. Okay. In case of mechanical waves, the disturbance will be in terms of displacement of a particle from its mean position. Now, polarization of a wave means restricting the disturbance to a particular direction. Okay, that is what we mean by polarization. Uh, the idea that you shared is also correct only. In sunglasses, there is polarization. Okay, that's correct. Basically, we are understanding the science behind that, what actually happens. Now, you consider a situation like this. Let's say there is a grill through which a string passes. Okay, you can see that the grill has, it has vertical grooves. Fine. So the string is allowed to oscillate parallel to the rods. Obviously, it cannot oscillate perpendicular to the rods because there's no space. Fine. Suppose you hold the string at this end, okay, at the left end, and you oscillate it. Okay. Now, if you oscillate one end of the string, what happens? A wave will propagate along the string. Suppose you complete one oscillation. Okay. You pull this particle up and down along the y-axis, means parallel to the rods of the grill. Then what will happen? You will generate a pulse like this, which propagates forward. Now, the way the grooves in the grill are arranged, Rishi, you tell me, do you think this pulse will be able to pass through the grill or not?
No.
Why not?
Oh, yeah, it will be able to.
It will be able to, okay? Because this pulse is disturbing particles in the y direction. And the grooves in the grill are also in the y direction itself. Fine. So this pulse will be able to pass through the grill to the other side of the string. Okay, fine. What if we generate a pulse by disturbing the particle of the string in the z direction? Like let's say you pull it this way and you oscillate it like this in the z direction. In the grill, you can see z direction is perpendicular to the grooves. So if you generate a pulse like that, will it be able to pass through this grill? So basically, you are creating a pulse parallel to the z direction. Do you think this pulse can pass through that grill? Or maybe I should show it like this, just a moment. Since we are looking at it from a particular angle. Let's say the particle was oscillated this way. Then the pulse you generate will kind of look like this. And as it propagates forward, what happens is this pulse tries to disturb particles of the string along the z direction. But in the z direction, the grill does not allow the string to move. Okay. Displacement in this direction is not allowed. So what will happen? The particles cannot oscillate in that direction. And as they cannot oscillate in that direction, this pulse, okay, the yellow colored one, will not pass to the other side. Is this clear?
Yes, sir.
Yeah. Any oscillation other than the ones which are parallel to y-axis will not pass through this grill. because the grill only allows the particles of the string to oscillate in the y direction. In fact, there's exactly one point of the string which is trapped in this grill. That point is restricted to oscillate only in the y direction. Okay, so if you create any disturbance which oscillates the particles in the y direction, only that disturbance can pass to the other side of the string, pass through the grill. Okay, so basically this is what happens in polarization. We restrict the disturbance to one particular direction. In fact, we can say we restrict the disturbance to one particular plane. Now you can say that the string is parallel to the x-axis. String is parallel to x-axis, so wave travels in the x direction, and oscillation is allowed only in the y direction. Okay, on the right side, you have polarized wave. The polarized wave particles can only oscillate in the y direction. We are talking about waves on a string. Okay, we still didn't discuss about light wave. So the particle oscillates in the y direction, wave propagates in the x direction. So basically we call this as a plane polarized wave. Which plane? The xy plane. These particles oscillate in the xy plane. Fine. What was originally being generated by the source is an unpolarized wave. Why do we call it unpolarized wave? Because the disturbance, oscillation, is not restricted to one direction. Okay. Once the particle was oscillated in the y direction. Another time or sometime later, the particle was oscillated in the z direction. Fine. Some other instant, it could be oscillated in some other random direction also. So a wave which has disturbances in different directions is called an unpolarized wave. But when you restrict the disturbance to one direction, you say it is polarized. Like in this example, after passing through the grill, the particles of the string oscillate only in the y direction, and the wave is propagating in the x direction. So we say that this is a plane polarized wave after passing through the grill. Okay. And see, polarization, like restricting the disturbance to one direction, can only happen in transverse waves. Okay, what are transverse waves? Transverse waves are waves in which the disturbance is perpendicular to the direction of propagation. Here, the direction of propagation is in the is along the x-axis or parallel to the x-axis. The disturbances are in the YZ plane. Okay, so we are disturbing the string particles in the YZ plane, but wave is propagating in the x direction. So what we are generating are transverse waves, and only transverse waves can get polarized. Longitudinal waves cannot get polarized. Okay. Now let us discuss about polarization of light. Or fine, we can go into further detail with this itself. Okay. Let me just copy this diagram. Okay. Now the grill that we have considered here allows oscillation only in the y direction. Okay. It doesn't allow the particle to oscillate in the z direction. And oscillation in x direction cannot happen anywhere because the string is in the x direction or parallel to x axis. So you look at it, you visualize it like this. Let's say you are looking at the grill from right in front. The string is passing through this point of the grill. Okay. So one particle of the string will be trapped in the grill. And that particle is the one which is only allowed to oscillate in the y direction, this way. You try to oscillate it in any other direction, it cannot. Okay. Any other means in the z direction, it cannot. Now, see, if you hold the first particle of the string and move it in the y direction, you generate a pulse or you generate disturbance in the y direction. That disturbance can pass. If you hold the first particle of the string and oscillate it in the z direction, it creates a disturbance in the z direction. It tries to disturb every particle in the z direction. Now, till the pulse reaches the grill, particles can get disturbed in the z direction also, but the grill restricts the movements of the particles. So on the other side, you will not see any displacement in the z direction happening. Okay. What if you disturb the first particle in a random direction between y-axis and z-axis? Let's say you created an oscillation like this. Then what will happen? That disturbance, the oscillation that you created, is basically trying to displace particles in both y and z direction. Okay, so what you are trying to do is you are trying to move particles of the string in a direction like this. Then if you create this kind of disturbance, if you try to oscillate the particle at an angle, Rishi, can you guess what will happen? Will the disturbance pass through the grill or not? Or will it get blocked completely, or will it partially pass? What will happen? Okay. When we try to disturb the particle at an angle like this, okay, when we try to displace it at an angle like this, what happens is only the component of displacement parallel to y-axis will be allowed to pass. So suppose you tried to displace it by an amplitude A. Okay. And let's say this angle is theta. Then what will happen? The effective displacement which passes through the grill will only be the component of the amplitude A in the y direction or in a direction parallel to the grooves in the grill, and that component will only be A cos theta. Okay, you are trying to move the particle up to a distance A in some random direction which makes an angle theta with the y-axis. But since the groove is in the y direction, the effective displacement of the particle will only be A in the y direction. Okay, so if you create a disturbance like this at an angle, okay, you oscillate the particles of the string. Till that disturbance reaches the grill, the particles will oscillate at an angle itself. But after passing through the grill, you will only see particles oscillating along the y direction with this much amplitude. So you will see the pulse pass like this. Okay, you tried to disturb it by an amplitude A, okay, such that it has an amplitude A, but the effective amplitude you can expect to pass through the grill is only A cos theta, where theta is the angle between the direction in which you oscillated the particle and the direction of the grooves in the grill. Okay, so basically this is a side view of what is happening. And this you can say is when you view it parallel to the x-axis. The view parallel to x-axis, because the string is in the x direction. Okay, it looks like a dot. You try to oscillate the particle in some random direction, only a component of the oscillation will be allowed to pass. Okay. Now consider a light wave, okay, unpolarized light. Basically, when you switch on any source of light, okay, you get a huge number of light waves from it. And there's no guarantee that all the waves emitted by a particular source, like a bulb or something, will have their electric and magnetic fields oscillating in the same direction. Suppose there is a beam of light traveling in the x direction. Okay, you use laser light if you want. Right? It travels in one direction, straight line. Let the light travel along the x-axis. Now, if light is traveling along the x-axis, means an electromagnetic wave is traveling along the x-axis, it means the electric and magnetic fields in it oscillate in the yz plane. Now, when a beam of light is traveling along the x-axis, beam of light is a collection of a huge number of waves. Some of those waves may have their electric field in the y direction, only in the y direction. Some of those waves may have electric field only in the z direction. Some may have electric field making an angle 45 degrees with y and z. Okay. So there will be a bunch of waves with electric fields in many different directions. So this is how we represent unpolarized light. Why is it like this? Just a moment. Okay. So what is happening here is that light is traveling. Okay, a beam of light is traveling in the x direction. The x direction here is perpendicular to your screen. The grill is in the YZ plane. This is Y axis. This is Z axis. Okay, we should no longer be calling it grill actually. Fine. Uh, let's say there is some material which allows light or which allows electric field only in the Y direction to pass through it. Okay. Assume this is something which allows electric field in Y direction to pass. In whichever direction the electric field is allowed to pass, that is called as the pass axis. Okay. So for this material that is there, okay, you can call this material as a polaroid. For this material, the pass axis is the Y axis. Okay. Now what is incident on it is unpolarized light. These red arrows that you see are electric field vectors of the many different waves which are present in this beam of light. Okay. One of the waves, as you can see, let me pull this aside first or copy paste. One of the waves has electric field of amplitude E naught in the Y direction itself, completely in the Y direction. One of the waves has electric field of amplitude E naught completely in the Z direction. Okay, the wave is traveling perpendicular to your screen, and as I said, perpendicular to your screen is the X direction. So electric field vectors of these waves will be in the YZ plane. So some of them have electric fields completely in the Y direction. Some of them have electric fields completely in the X direction, but the others have electric fields in different directions. Let's assume they all have the same amplitude E naught. Okay, but directions will be different. So this is what is unpolarized light. Now what happens when this unpolarized light passes through this material? This material is called a polaroid. So polaroid has this ability to restrict electric field to one direction. It will cut off electric field in the other direction. So assume this polaroid allows electric field only in the Y direction to pass. It cuts off the Z component of the electric field. Only Y component is allowed to pass. Then what will happen is, uh, for one of these waves, the entire electric field is in the Y direction. So that wave will pass as it is, this one. But for the remaining waves, only a component will be allowed to pass. And you can visualize components like this. Okay. One wave has its electric field completely in the Y direction. That wave's electric field will pass as it is, this way. Another wave, okay, or the other waves only have components in the Y direction. So their components only will be allowed to pass. Like the second one, if you see, its electric field is only this strong. So for the second wave, a smaller amount of electric field will pass through the polaroid. Let's say the second wave makes an angle theta, okay, or theta 1 with the y-axis. So one electric field that passes is E naught. The next electric field that passes is E naught cos theta 1. Then the third wave you consider, assume it makes an angle theta 2 with the y-axis. How much will its component be? E naught cos theta 2. And that component is what is allowed to pass. So another electric field like this will pass through that axis. That electric field's magnitude is E naught. Okay, maximum magnitude is E naught cos theta 2, and so on. So different waves of this unpolarized light, okay, different waves which are components of this unpolarized light will have different amounts of electric field passing through the axis. The third wave, the third or fourth one, you can say makes an angle theta 3 with the y-axis. Then its component that passes will be E naught cos theta 3, a smaller amount of electric field. And so on. The other wave that we have considered, the remaining wave, has its electric field completely in the z direction. If electric field is completely in the z direction, it has no y component at all. That means that wave gets cut off completely. That electric field gets blocked completely. Okay. So what passes through the polaroid is only electric field in one particular direction. The incident light had electric fields in many different directions. After passing through the polaroid, you will be able to see electric field only in one direction. That is the direction of the pass axis of the polaroid. That's the direction in which it allows the electric field to pass. See, light is an electromagnetic wave. There is a magnetic field also associated with it, but we don't talk in terms of magnetic field. Okay, we just talk in terms of what happens to the electric field. So electric field will be allowed to pass parallel to the pass axis. And if there is electric field this way, there is magnetic field perpendicular to it also. We don't talk about that. Okay. Now in the incident light, okay, unpolarized light was incident. What comes out is polarized light. In the incident light, all the waves had the same amplitude of electric field E naught. Okay. Therefore, intensity of incident light, okay, you can call it as I naught, will be, we know intensity of a wave is proportional to square of its amplitude. Okay. And in fact, we had derived in the chapter electromagnetic waves, we derived a formula also for intensity of electromagnetic wave, half epsilon naught E naught square into C. So intensity is proportional to square of amplitude of electric field. Okay. Proportionality constant, that half epsilon naught C, let's call it as K. So you can write intensity of incident light is K E naught square, average intensity of the incident light. Okay, which is unpolarized. Now, once it gets polarized, you can see all waves don't have the same strength of electric field now. One wave has E naught, the next wave has E naught cos theta 1, next has E naught cos theta 2, and so on. And theta varies from 0 degrees to 90 degrees. Fine. So if you want the intensity of polarized light, light that comes out of the polaroid, what you will have to do is K multiplied with average value of square of amplitude of electric field you have to take. Okay. Now, different waves have electric fields making different angles with the y-axis. So electric field in y direction, we can generalize it as E cos theta. For one wave, it is E cos theta 1. For another wave, it is E naught cos theta 2, and so on. So we'll treat theta as a variable. So the electric field that passes through the polaroid is E naught cos theta, where theta is the angle made by the wave with the pass axis of the polaroid. So if you want the intensity of light that comes out of the polaroid, you will have to average E naught square cos square theta. Because the amplitude is now E naught cos theta, you square it and you have to average it. Okay. E naught square is a constant, put it outside. Average value of cos square theta. Rishi, do you remember the average of cos square theta in the interval 0 to 90 degrees?
No, sir, I don't remember.
Okay. We had derived this in alternating current. Average value of sine square theta or cos square theta in one time period or half time period will be 1 by 2. Okay. Therefore, the intensity of polarized light, okay, that passes through the polaroid is half K E naught square. Now, what was K E naught square? Intensity of incident unpolarized light. Then what comes out, the intensity that comes out of the polaroid is exactly half of the intensity that is incident on it. Okay. This is what sunglasses do. You know sunglasses involve polarization, right? And why do we use sunglasses? To block sunlight, but not completely. Okay. When the light is very bright, you see through the sunglasses, you won't feel it that bright. Okay. You won't feel it that bright means the intensity is getting decreased. And this is exactly what happens when light passes through a polaroid or sunglasses also. Incident light, let's say it has intensity I naught, okay, the sunlight that is falling on it. After passing through the sunglasses, the intensity becomes I naught by 2. So only half the brightness will be entering into your eye, which makes it more comfortable to see. Okay, so remember this point. If unpolarized light is polarized, the intensity becomes half. Okay, and polaroid is one material which can polarize light. How does it do that? Polaroid has long chain molecules. Okay, which molecule exactly? I don't know. It has long chain molecules. What these long chain molecules do is they absorb electric fields, and they absorb electric fields parallel to the molecule. So if the polaroid is allowing electric field in the y direction to pass, it means the molecules of the polaroid, the long chain molecules that are there, must be in the z direction. Why? Because then they will absorb the z component of electric field. Whatever component is there parallel to the molecule will get absorbed. Okay, polaroid has molecules which have the ability to absorb electric field parallel to themselves. So if molecules are arranged in the z direction, the z components of electric fields will all get absorbed. Only the y component will be allowed to pass. That is how a polaroid works. Is this clear?
Yes.
Okay. So if unpolarized light is polarized for the first time, its intensity becomes exactly half. And see, here we are viewing along the x-axis. The wave is also traveling along the x-axis. That is why you see its electric fields in the y direction and z direction, or in the yz plane. But usually in diagrams, they don't represent it like this. Suppose an electromagnetic wave is traveling this way. Assume this is the x direction. Then electric field will be in the yz plane. Means its electric fields will have y components and z components. So how they represent that is they show arrows and dots. If there's an arrow this way, it means there is electric field in the y direction. And if there is a dot here, it means it has electric field in the z direction as well. Wave is going in the x direction. Electric fields are present in the y and z directions, means it is unpolarized light. Okay, that is how they denote unpolarized light in diagrams. Arrows and dots. Arrow indicates electric field perpendicular, in the y direction. And dot indicates electric field in the z direction, that is perpendicular to your screen. Right. So this light is unpolarized light. Suppose it got polarized, and let's say the electric field was allowed only in the y direction, the z component was cut off. Z component cut off means what? The dots should not be shown. Dots represent electric field in the z direction, perpendicular to your screen. Let's say wave direction is the x-axis. Okay, so out of your screen or perpendicular to your screen will be the z-axis. Now suppose this light was polarized and electric field was allowed to pass only in the y direction. Z component was cut off. Then how you should represent it is, or how they show it to you in the diagrams is like this. They won't show you these dots. That's all. So this is polarized light. and it is polarized along the y-axis or in the y-x plane, xy plane polarized light. Okay, the electric field is allowed only in the y direction. Suppose it is polarized and electric field is allowed only in the z direction, then you would have seen, then you will have to show it this way. Only dots will be shown. Means there is electric field only in the z direction, no electric field in the y direction. So this also indicates polarized light. Right. So whether you show only arrows or only dots depends on the direction in which the light is polarized or the direction in which electric field is allowed to pass. Okay, so what all have we discussed? So basically, what is polarization? Restricting the disturbance to one direction is what we call polarization. It can be done only in transverse waves. Okay, and the fact that light is getting polarized proves that light waves are transverse waves. Okay, so experiments based on polarization proved the transverse nature of light waves. YDSC, single slit diffraction, they proved that light has wave nature. What kind of wave it is was proved by experiments based on polarization. Okay, the fact that light is getting polarized proves that it is a transverse wave. Okay. Then we discussed what happens to intensity when unpolarized light is polarized for the first time. Fine. Okay, just a moment. I'll give you another diagram. Okay, consider a situation like this. Assume this is a polaroid. Its pass axis is the y-axis. Means it allows electric field in the y direction to pass through it. Now, if light is unpolarized, you will have electric fields in different directions in the YZ plane. Okay, we are assuming the wave is traveling in the x-axis perpendicular to your screen. So electric fields will be in random directions in the YZ plane. Once it gets polarized, no? Okay, let's say it has been polarized by a polaroid whose pass axis was the y-axis. Then you will have electric fields remaining only in the y direction. They'll be of different strengths. For some waves, the entire electric field was allowed to pass. For some waves, the Z component was cut off and only a component along the y-axis was allowed to pass. Okay. So once the light is polarized, you will have electric fields like this. Okay, the red arrows that you see. So basically, this is polarized light. You imagine this polarized light being sent through this polaroid once again. Okay, light that has been polarized in the y direction. Assume it is again made to pass through a polaroid whose pass axis is the y direction itself, y-axis itself. Rishi, you tell me now, will this polaroid do any filtering or will it allow this light to pass as it is?
Will allow it to pass, sir.
It will allow it to pass as it is, right? So already polarized light, if you pass it through another polaroid such that the pass axis is parallel to the axis in which the electric field exists, then the light will pass as it is. So if this intensity is I, if the incident polarized light's intensity is I, and the polaroid is arranged this way, it allows all the light to pass through it, then the light that comes out of the polaroid will also have the same intensity I. There's no removal of electric field happening. There's no blocking of electric field happening. So the same intensity will come out. Did you understand this or not? Rishi, is this clear?
Yes, sir. Yes,
Okay.
sir.
Okay. Now consider something like this. Let's say, okay, let's consider this same polarized light. It has been polarized in the y direction. Okay. Assume it is made to pass through a polaroid whose pass axis is not the y direction now. Let's say the Polaroid is rotated a little bit. Maybe like this. Okay. So assume the pass axis of this Polaroid makes an angle theta with the y axis. Right. Now, if this already polarized light is made to pass through this Polaroid, Rishi, you tell me, will any blocking of electric fields happen or will it be allowed to pass as it is?
Sir, it won't be allowed to pass. There will be some filtering.
Some filtering will happen, but will it allow any light to pass or not? Or will it block it out completely?
Some light will be passed, sir.
Some light will pass, good, because some components can pass through it. The angle between the, what do you say, the direction of polarization of the light and the pass axis of this Polaroid is not 90 degrees. So components will be there. Now let's say the incident light, which is already polarized, has average electric field E. Okay. Incident light has average electric field amplitude E. Now what you are doing is you are allowing components in this direction to pass. This is the pass axis of the Polaroid, which makes an angle theta. If you are allowing those components to pass, that means the average component that you are allowing to pass through the Polaroid, average amplitude that you are allowing to pass through the Polaroid is E cos theta. Okay, so you will see something like this passing through the Polaroid now. Is this clear?
Yes, sir.
So basically what we are doing is light which has been polarized in the y direction, we are polarizing it in some other direction now. But when you do that, you will lose some intensity, some more intensity loss will happen. Okay, let's say the incident polarized light had an intensity I. Then the light that comes out of the Polaroid will have some other intensity now. And we know intensity is proportional to amplitude of electric field. So I you can say is K E square. And the intensity that comes out, okay, you can call it I dash, will be K E cos theta whole square. This time theta is not a variable. Okay. What was incident is already polarized light. So all electric fields in the incident light were in the same direction. And they all make the same angle with the pass axis. Okay, so theta is not a variable this time. So the intensity that comes out of the Polaroid will be K E square cos square theta. And K square is the incident intensity. So you get I dash is equal to I cos square theta. So if already polarized light is passed through another Polaroid, this is what happens to intensity. Where I is the intensity of already polarized light that is incident on it. And theta is the angle between electric field of the incident light and the pass axis of the Polaroid. Then the intensity that comes out will be I cos square theta. This is called Malus's law. Very important from exam point of view. Questions based on this are quite common. Okay, so when polarized light is again passed through a Polaroid, you can find out the effective intensity this way. See, when unpolarized light is incident, no, different electric fields were in different directions. So there, when you take component E cos theta, theta is a variable. But if already polarized light is incident on another Polaroid, in the already polarized light, all electric fields were in the same direction. Then they'll all make the same angle with the pass axis. So this time theta will not be a variable, so you don't have to average it. You take cos square theta as it is. Okay. Let's solve one problem based on this. Suppose there are two Polaroids. Okay, one placed on top of another. One is this. The other one you assume is this. Okay. One of them has path axis as the y-axis itself. The other one's path axis makes 45 degrees with the y-axis. So these two polaroids are rotated by a relative angle of 45 degrees. They have their path axis rotated by 45 degrees. Rishi, is the picture clear?
Yes, sir.
Okay. So there are two polaroids arranged like this. Suppose unpolarized light of intensity I naught is incident on this combination. Okay, it passes through one polaroid, then it passes through another polaroid also, and then comes out on the other side. So unpolarized light of intensity I naught is incident. Find out the intensity of emerging light. What is the intensity of the light that emerges from this set of polaroids? These two polaroids have a path axis, have an angle of 45 degrees between their path axis. Okay, think carefully. Incident light is unpolarized, passes through one polaroid, then it passes through the other polaroid also, and then emerges out. Right. Okay. Let's consider the polaroids one by one. Take this one first, which has its. Okay. Consider this one, which has its path axis parallel to the y-axis. Now, if unpolarized light is incident on this, what will happen? Electric field only in the y direction will be allowed to pass, and it's getting polarized for the first time. So unpolarized light intensity, let it be I naught. Rishi, you tell me, when unpolarized light is polarized for the first time, what is the intensity that emerges? When
Uh,
huh.
K E naught square.
No, not in terms of electric field and all. If the intensity that is incident on it is I naught, and this is unpolarized light, after it gets polarized for the first time, what happens to its intensity? It gets halved. Okay. When unpolarized light is polarized for the first time, the intensity becomes half exactly. Okay. It doesn't matter how you arrange the polaroid also. Okay, the intensity will become half, because in whichever way you arrange the polaroid, the electric field vectors will be making random angles only. Okay, so you'll have to take the average of cos square theta, it will become half I naught. So unpolarized light of intensity I naught, if it is polarized for the first time, the intensity becomes I naught by 2. And what is incident here is unpolarized light, such as this. Having intensity I naught. What emerges out of this polaroid is polarized light, such as this one. Is this clear? You will have electric
Yes.
fields only in the y direction. Okay. Now, this already polarized light is being passed through another polaroid. This already polarized light, now its intensity has become I naught by 2. Okay. You can call it as I if you want. It's half of the original intensity. Now, this is being passed through another polaroid. And that other polaroid has its path axis making 45 degrees with the y-axis. So what will happen? Will it get filtered some more or not? What do you say? What is incident is light with electric field oscillating this way. It will get filtered, and what will be allowed to pass is only this component of electric field. Like this. Okay. So the intensity, the amplitude decreases further, the intensity decreases further. Now, what is the angle between the existing electric field and the pass axis here? The existing electric field is in the y direction. This makes 45 degrees. So the angle between them is 45 degrees. So basically what is happening? Already polarized light of intensity I is being passed through another polaroid whose pass axis makes 45 degrees with the electric field of this light. Then what should happen to intensity? Malus's law. It should become I cos square 45 degrees. Cos 45 is 1 by root 2, cos square is 1 by 2. So the intensity that comes out will be I by 2. And I is already I naught by 2. So the effective intensity that emerges is I naught by 4. Okay. The first polaroid makes the intensity half. Okay. The second polaroid is further decreasing it by half. So the final intensity of light that emerges out of the two polaroids is I naught by 4. Is this clear?
Yes, sir.
Okay. Suppose we have 3 polaroids this time. Think carefully and answer. I'll give you time. Let's say this is one. Another one is this, whose pass axis makes 45 degrees with y-axis. So one Polaroid's pass axis is the y-axis itself. Another Polaroid's pass axis makes 45 degrees with y-axis. And a third one, let's say its pass axis is parallel to x-axis. Just a moment. Okay. Okay. There are 3 Polaroids like this. Fine. And assume unpolarized light is incident. This is the first Polaroid. Second one making 45 degrees with the first one. Third one making another 45 degrees with the second one. Or you can say third one makes 90 degrees with the first one. Okay. So assume unpolarized light of intensity I naught is incident. Rishi, tell me, what will happen to the intensity after it passes through the first Polaroid?
Right,
Then,
it's not polarized, right?
incident light is not polarized. So the first
So
time
it'll
it
become
gets,
half.
it becomes half, correct. So I naught by 2 is what emerges from the first Polaroid. Good. Now the second one makes 45 degrees with the first one. So what will it do to the intensity?
It'll
Incident,
become I naught by 4.
incident light was unpolarized. This is polarized now, but again it makes 45 degrees. So yeah, what you said is correct. It becomes I naught by 4. This is also polarized itself in a different direction. Okay, at 45 degrees with the y-axis, it is polarized. Now that light which is polarized at 45 degrees with the y-axis is passed through another Polaroid now. What will the third Polaroid do to the intensity? The second Polaroid restricts electric field to this direction, which is basically 45 degrees with the y-axis. The third Polaroid restricts electric field to this direction, which is 90 degrees with the y-axis. So what will the third Polaroid do to the intensity?
I
See,
naught, will it become I naught by 6?
how can it become I naught by 6? What formula are you using?
Sir, so half means I naught by 8.
It gets halved. Why it gets halved also we can discuss. The second Polaroid allowed light at an angle 45 degrees with the y-axis. That light's intensity was I naught by 4. What the third Polaroid is doing is it is further trimming it down. Okay. And what is the angle between the pass axis of the third one and the electric field in the second one? 45 degrees. So apply Malus's law. The intensity that finally emerges will be the incident intensity on the third Polaroid is I naught by 4 cos square. Angle made by the pass axis with the electric field is 45 degrees. Because the angle is again 45 degrees, cos square 45 again becomes 1 by 2. The intensity that emerges will be I naught by 8. Is this clear? Any doubts in
Yes,
this?
sir.
Okay. Okay. Fine. So using a Polaroid is one way of polarizing light. Fine. How does a Polaroid work? It has long chain molecules. Those long chain molecules absorb the electric field parallel to their length. They only allow electric field perpendicular to their length. Fine. And that perpendicular to their length, that direction is what we call the pass axis, which in this example is y-axis. Molecules are in the, okay, I should say z direction actually. You can see this is y and we considered this as z. Molecules were in the z direction. So z component of electric field is absorbed, only y component is allowed to pass. Okay. There is another way also to produce polarized light. Okay. We call that as polarization by reflection. Okay. Just a moment. Okay. Assume this is some medium which allows light to pass through it. Let's say the other medium is air, and this could be glass or something. Let's assume it's glass itself. You know, glass is a denser medium compared to air. Okay, we're talking about optical density. Suppose a ray of light is incident on the interface between air and glass. Now, whenever there is a medium change, okay, or whenever a wave traveling in one medium is incident on another medium, not just light wave, it could be any kind of wave. What happens is some energy carried by that wave enters into the second medium. Okay, it could get absorbed, it could get transmitted, and some energy gets reflected back into the first medium. Now here we are talking about light. When light enters from air into glass, refraction occurs and it is going from rarer medium to denser medium. So it should bend towards the normal like this. Okay, this is the refracted ray. But whenever a wave is incident from one medium onto another medium, reflection will also happen. You cannot avoid that. Okay, you can minimize it, but you cannot totally avoid it. So reflected wave will also be there. That follows the laws of reflection. Okay. Now for this particular angle of incidence, you know angle of reflection should be same as angle of incidence, and we got this as the angle of refraction. And there is some angle between the incident, there is some random angle between the reflected ray and the refracted ray. Okay. Now you increase the angle of incidence. Okay, or you change the angle of incidence. When the ray is incident like this, what happens? The reflected ray will go like this. Fine. Following the laws of reflection. And the refracted ray could, like it, there's a possibility that it goes like this. Okay. It has bent towards the normal. It's going like this. So what we are considering now is the case where the refracted ray is perpendicular to the reflected ray. That is also possible. Okay. For one particular angle of incidence, this will happen. Fine. Let's only consider that angle now, that ray now. Sorry. Okay. So we are considering the situation where reflected ray is perpendicular to the refracted ray. Okay. The angle of incidence which makes this happen is called Brewster's angle. So basically, what is Brewster's angle? The angle of incidence for which reflected ray is perpendicular to refracted ray. Okay. We can apply some knowledge of ray optics and find out this or derive an expression for this Brewster's angle also. Suppose the medium in which the incident ray is traveling has a refractive index mu1 and the other medium has refractive index mu2. Okay. Air's refractive index is 1, but we'll derive a general relation. Okay. Now here, this is the angle of refraction. Angle of refraction, I'll write it as RF. And angle of reflection, I'll just call it R, which is same as I. Okay. Now the angle between reflected ray and refracted ray is 90 degrees. That means angle of refraction RF should be 90 degrees minus angle of reflection R. Because if this is R and this is 90 minus R, only then this can be 90. Because total angle in a straight line is 180. 90 here gone, then these should be R and 90 minus R. Okay. So if angle of reflection is R, then the angle of refraction should be 90 minus R for this to happen. Let us now apply Snell's law. Rishi, tell me the equation for Snell's law.
Mu1 sin I is equal to mu2 sin R.
Good. Mu1 sin I is equal to mu2 sin R, where R is the angle of reflection. So refraction. I'll write it as RF, okay, just to avoid confusion. So we can say that mu1 sin I. The angle of incidence here is Brewster's angle. That is what we want to derive an expression for. So mu1 sin of theta b stands for Brewster's angle, is equal to mu2 sin angle of refraction. Now what is angle of refraction here? 90 degrees minus angle of reflection. Angle of reflection is same as angle of incidence, which is the Brewster's angle that we are talking about. That's all. Therefore, mu1 sin theta b should be equal to mu2 sin 90 minus theta b becomes cos theta b. That's all. Keep the theta terms on one side. You get tan of Brewster's angle is mu2 divided by mu1. So if the incident ray is incident at this angle, what angle? Tan inverse of mu2 by mu1. If incident ray is incident at this angle, you will see reflected light being perpendicular to refracted light. Is this clear? Did you understand the derivation?
Yes, sir.
Okay. Now let's consider air and glass itself. Air's refractive index is 1. Glass refractive index is 3 by 2. Okay. Calculate Brewster's angle. Calculate Brewster's angle when light is incident from air onto glass. Air refractive index 1. Glass refractive index 3 by 2. Do this quickly. See, light is incident from air onto glass. So this will be mu1 and this will be mu2. Direct application of the formula. The answer will be tan inverse mu2 by mu1, 3 by 2 divided by 1. So tan inverse 3 by 2, that's all. You don't have to tell the exact angle. Is this clear?
Yes.
Okay. So if light is incident at this particular angle, tan inverse mu2 by mu1, you will find reflected light being perpendicular to refracted light. So what? See, when this happens, when reflected light is perpendicular to refracted light, what you observe is, or what is observed to happen is, that the reflected light is polarized. Okay. So when the angle of incidence is the Brewster's angle, the reflected light that is there, okay, that you get will be polarized. How exactly or in which direction is it polarized? That also you can tell. See, incident light, assume it is unpolarized. Unpolarized light will be indicated by dots and arrows, as I said. So it has electric field oscillating in random directions. So incident light is unpolarized. Fine. When it is incident at Brewster's angle, the reflected light will be polarized. And in which direction does it get polarized? Only the dots are allowed to pass. This is what you will observe. So basically what is happening, in the plane of your screen, whatever electric field is there, that component is getting cut off. So you can say that the component of electric field in the plane of incidence, this whole plane is called the plane of incidence. That component gets cut off. The component perpendicular to the plane, the dots, will be allowed to get reflected. Okay. What about the refracted light? Refracted light will be partially polarized. Means some electric fields will be cut, some electric fields will be allowed to pass as it is. It won't be perfectly polarized. Refracted light will be partially polarized. So refracted light can be shown like this. At some places you may see only dots, some places you may see only arrows. It's partially polarized. Okay. But reflected light will be perfectly polarized. Is this clear? Now, why or how exactly this happens, you don't have to know. You just need to know what happens. So when unpolarized light is incident, on the interface between two media at an angle equal to the Brewster's angle, you will see reflected light being perpendicular to refracted light. And when that happens, the reflected light will be polarized. You have to imagine the direction in which it gets polarized also. Only the component of electric field perpendicular to the plane of incidence will be present in the reflected light. Okay, so this is what we call as polarization by reflection. So remember these two methods of polarization. One is by using a polaroid, the other one is by reflection. Okay, but this happens only when the incident light is incident at an angle equal to the Brewster's angle. Rishi, is this clear?
Yes, sir.
Okay. There is another way of polarization also. It's called polarization by scattering. This is what happens with sunlight in the atmosphere. Okay, and this is the reason the sky appears blue to us. Okay, see, what is incident on the atmosphere is sunlight. Sunlight is a combination of all colors, all wavelengths, all visible wavelengths. So, and it's unpolarized light. So suppose sunlight is incident this way. Light is traveling this way. So there will be dots and arrows. and so on. Now, when sunlight hits the particles in the atmosphere, what happens is light gets scattered in different directions. So let's say this is some random particle in the atmosphere. It gets scattered in different directions. The light that is scattered most, okay, or the light that is scattered by approximately 90 degrees will be polarized light. And it's in this direction, so only dots will be allowed to pass. Okay, and out of all visible colors, the color that gets scattered most is blue. So blue light is polarized, you can say. Okay, and because of this scattering, the sky appears, I mean, because blue gets scattered the most, the sky appears blue to us. Now, why exactly does that happen? If you assume this is the Earth's surface, let's say there's a person standing here. Now, if you have ever noticed, the sky appears blue right above your head, especially during sunrise and sunset. Midday, when the sun is above your head, the sky doesn't appear that blue, it appears almost whitish. Okay, but in the mornings, the sky close to the sun will appear reddish. The sky which is overhead, exactly above your head, will appear blue. Why that happens is because, see, assume the sun is here. Sun, as I said, emits light of all colors. Okay, so I can't show a particular color here. I'm showing it in black. Sunlight is a combination of all colors. Now, the light that reaches you directly from the sun has to be light which is least scattered. Okay, the sun is just up, just rising here. Okay, it is just above the horizon. So the light that reaches you directly from the sun has to be light which is least scattered. And out of all visible colors, the color which is least scattered is red. That is why in the mornings the sun appears red to you. Okay, it's not because sun only emits red color, or it's not because sun is actually red in color. Okay, early in the morning, the light that reaches you from the sun is the least scattered light, which is red. Now, sunlight is emitted in all directions. No, so there are particles in the atmosphere. Now, some of these sun rays, what will happen? They may strike some particle in the atmosphere here and get scattered and then enter into your eye. Okay. Now, the light entering into your eye from above, means from the overhead direction, has to be the light that is scattered most. Okay, it has to have a large angle of scattering. Fine, and the color that is scattered most is blue. So what you see entering, what you feel entering into your eye from these directions is blue. Okay, so when you look at the sun directly, sun appears red because that is least scattered light coming into your eyes. And when you look up at the sky, you are able to see the sky due to scattering of light, sunlight only. Okay, sunlight falls on dust particles in the atmosphere and gets reflected or scattered into your eye. Now, the light that enters into your eye from above your head is the light which is most scattered, and the light which is most scattered is blue. Okay, so during this scattering also some polarization will occur. That is called polarization by scattering. Okay, that's all you need to know about polarization. Solve a few problems based on this and be thorough. Next class, we'll start the next chapter, dual nature of radiation and matter.